Assalamu alaikum. So in this lecture, we'll discuss the vector control of the induction motor, and we will study in detail the rotor field-oriented control. Now, first of all, I need to highlight with you why we need vector control. Before we are using, let's say, scalar control, and this is actually the closed loop V over F. It was simple, but it's not very accurate. So in the high performance drive system, we need to use more precise control where oscillation is not recommended. So we need to use a vector control. And for that, one of the famous vector control for the induction machine is the rotor field-oriented vector control. And the idea behind the rotor field-oriented can be understood by the following. Let's assume that this is the AS and this is the BS and this is the CS. Those are the stator stationary reference frame, and simply let's assume that here we having the AR, here we have the BR, and here we having the CR. Those are the axes for the rotor that's rotated by omega r. So this angle is theta r, which equal to the integration of omega r d tau plus theta r of 0. Now recall in the synchronous rotating reference frame, all the sinusoidal signals are seen to be constant. So the rotor flux will be constant, rotating by omega e speed, the synchronous speed. And this is lambda r, the rotor flux. So this is the rotor flux. And by assumption, let's assume that omega r is constant. Although in the stationary reference frame it's alternating, but simply in the synchronous rotating reference frame, any sinusoidal signal rotating by the synchronous speed is seen as constant. So this one I can write here as a note for you. In synchronous rotating reference frame, the sinusoidal signal are seen as constant signals. So now in the reference frame, in the D or QD reference frame, we have two orthogonal frame. We can attach it anywhere in space. Let's assume we are lucky and we manage to attach the D axis of the reference frame in the same direction of the rotor flux. So this will be the DRE, and ahead of that, 90 degree ahead of that, here will come the QRE. Now here E is referred that the reference frame is rotating by synchronous speed. So if this is the case, what will happen? Now, in general, we know that lambda r as a vector has two components, one in the direction of the dx and the other in the direction of the qx. So here we have lambda q r e as a vector plus lambda dre as a vector. Now, due to our selection, then this component will go to zero because all the flux is directed toward the dr, and we will end to lambda dre is equal lambda r, which by assumption is a constant. So let's repeat here. If we can manage to elegant our reference frame, the d-axis of the reference frame, which in general we call the field axis. In the direction of the rotor flux, so this is the lambda r, we get lambda q r e is equal to 0, and lambda d r e is equal to lambda r, which is by definition is constant, or simply by assumption. By assumption. We are assuming that what the rotor flux is fixed, so simply this can be a constant flux. So now let's see what will happen to the voltage equation in the QD reference frame. So now I will recall the voltage equation of the rotor under field-oriented vector control. So first let's write the VQ RE, which was equal to RR IQ RE plus d by dt of lambda q RE plus omega E minus omega R lambda d RE. This is the first question. And we have the VDRE, which equal to RR IDRE plus d by dt of lambda DRE minus omega E minus omega R lambda Q RE. So under field-oriented vector control, and the assumption that we have either squirrel cage configuration for the rotor or one rotor where the slips are shorted, simply we will have VQRE is equal to VDRE, which equal to 0. So let's see what will happen to the first equation here. So 0 will equal to RR IDRE plus d by dt of lambda DRE minus omega slip lambda QRE, where simply this one is actually is omega slip. Now, under the assumption that lambda r is the direction in the DRE, lambda QRE is equal to 0. So this term is equal to 0 by our assumption. And by our assumption that the rotor flux is constant, so d by dt of the constant is also a 0. So we end up with IDRE is equal to 0. Now let's see what will happen to the second equation, VQRE, to this equation. And I will take it here. So we have VQRE, which equal to R IQRE plus d by dt of lambda QRE plus omega slip multiplied by lambda DRE. So 0 equal to RR IQRE plus. Now this term is equal to 0 by assumption because lambda QRE is equal to 0, and we end up with omega slip lambda DRE. So from here we can write omega slip as minus RR IQRE over lambda DRE. Now in general we need to write omega slip in terms of something we can measure, which is the stator components actually. So let's recall the flux linkage for lambda QRE is equal to LR IQRE plus LM IQSE. Now this by assumption is equal to 0. So from here we can write IQRE is equal to minus LM over LR IQSE. And the flux linkage in the direction of the D, so lambda DRE, is equal to LR IDRE plus LM IDSE. Now we know that from the vector orientation that IDRE is equal to 0. So we end up with lambda DRE, which equal to lambda R equal to LM IDSE. Now we can substitute the value of lambda DRE and the value of IQRE in omega slip, so here and here, and we will end up with omega slip is equal to RR over LR IQSE over IDSE. Now we know that this one is 1 over tau r. So we can write here omega slip is equal 1 over tau r IQ SE over IDSE, where tau r is the rotor time constant, electrical time constant. So tau in general is equal L over R. Now we have this relation for omega slip. Let's see what will happen in the torque. Now recall that the electromechanical torque Te for the induction machine in the QD reference frame can be written as 3 over 2 due to the transformation P over 2 L M over L R IQ SE lambda D RE minus ID SE lambda Q RE. Now recall in the vector control, lambda QRE is equal to 0. So this term is equal to 0 because all the flux is elegant to the D axis. And simply we'll end up with TE is equal to 3 over 2 P over 2 LM over LR IQ SE lambda D RE. And recall lambda DRE was equal to LM I DSE. This one here. So to this end, the electromechanical torque of the induction machine in the QD reference frame, in the field-oriented reference frame, in the rotor field-oriented reference frame can be written as TE is equal to 3 over 2 P over 2 LM over LR square IQ SE IDSE. Now those are constant, so simply this means that TE is proportional with IQ SE IDSE, and it's very interesting actually. So to summary, we have the following under the field oriented control. We have lambda D RE is equal to L M I D S E, and we have the torque TE which equal to 3 over 2 P over 2 LM square over LR IQ SE ID SE. And as we stated later, this term is constant, so TE is proportional with IQ SE ID SE. Now if we recall the TE of the DC motor, where TE is proportional with IA IF. So now we can say that IDSE is the field component of the current, of the stator current, while the IQSE is the torque component of the field of the stator current. The torque component of the stator current. So now the induction machine can be controlled as easy as a separately excited DC machine, and this is very interesting. So now, in order to implement the vector control, we need the knowledge of theta E. So simply, we have the